All right, continuing on with our per pixel collision detection mini-series. In this video, it's time for us to get started on an application that's going to serve as a proof of concept for everything that we've talked about so far in regards to checking if one pixel has collided with another between two different sprites. Now, before Logan begins the coding process, I wanted to spend one more second on the whiteboard and shuffle around our rectangles just a little bit. What I'm talking about is there may have been some of you guys in the last video watching us walk through our little formula for calculating x1, y1, x2, and y2 and thinking to yourself, oh, sure, that worked perfect because you happen to have your corner edges so nicely laid out. Look at that. They're at corners. One is at the corner of box B and the other one is at the corner of box A. So from grabbing the two sprite corners, ta-da, we've got our new rectangle. But what happens if we happen to shuffle around these sprites where the intersection happens at some other location where we don't have these convenient corners? Will our formulas down here still work? And the answer is yes. And I just wanted to show that real quick without spending a lot of time walking through it. So let's go ahead and throw a new layer in here real quick. And we will hide this one out. And check it out. What if we had the following scenario? So let's say that we've got sprite A down here and sprite B up here. And sprite B happens to be just a little bit narrower. Now, our upper left-hand corner, our x1 and y1, and our x2 and y2 are no longer on convenient points like we had before. And that's why in the last video we said, you really need to think in edges, not in points. Okay? So, but check it out. It still works. Remember, we start on the left-hand side, so it's left, then top, then right, and then bottom. So starting on the left-hand side, comparing our two edges, it is going to be the edge that is the greatest in x. Okay, so our two left-hand edges, the one that's greatest in x, that will be this guy right here. Then we're going to shift to the top, and we are looking for y that is the greatest. So we've got our two tops, and the largest y, of course, going down. Y gets larger and larger, as we all know, so that means this edge is going to be our winner. That's the largest of the two in y. Then we're going to shift over to the right-hand comparison, so we're comparing the two right-hand edges, and once again, we are looking at x, but we're looking for the one with the lower x, the one closer to the left-hand side, as I said in the last video. So this guy right here has got the smaller x, because this guy over here obviously is going to be a larger x because x is getting bigger. So that means we've grabbed this edge right here. And then finally we're going to move around to the bottom. Comparing the two bottoms, we are looking for one with the lower y value. That's the guy that's going to be closer to the top of your screen. So here is our lower y value. As working our way back up, y is getting smaller. So where do all of these guys cross? Well, lo and behold, right here. And that information would have given us, so right here would have been our x1 and our y1, and then down here would have been our x2 and our y2, and that would have defined this new box. Okay? So there you go. I just wanted to show you flipping A and B around to a less convenient location that we could still, utilizing the same formula, demonstrate that we did indeed have a collision. Okay?
Right, just pointing out that using that opposing edge calculation does indeed allow us to grab the intersection rectangle no matter what the orientation of sprites A and B.
Exactly. Now, with that out of the way, Logan, let us jump over to Visual Studio.
All right, let's get started on a project. So, here in Visual Studio, we'll begin the project for this per pixel collision test. We're going to make sure that this is an XNA 2 game, and we can call this per pixel collision.
Now, as Logan's typing that in, let me let you guys know we are going to break this up into 3 videos just so that we can keep the content very focused on what we're doing. So the goal of this video is by the end of everything, we're going to have, and everything meaning this video, we're going to have a sprite that is centered on the screen and a sprite that we can move around with the mouse. And as the two sprites intersect with one another, we're basically going to draw an orange rectangle.
Exactly. We're going to draw a visual representation of that intersecting rectangle.
Exactly.
All right, so project name per pixel collision looks good. We'll begin the project. And then we're going to need 2 folders added. We'll need a folder for classes and a folder for textures. So I can add a classes folder to the project. And within the content subproject, I can add a textures folder. Now we have some image files to place inside of the textures folder, which I have located out in our working directory. I could load those up real quick and point out what they are. We have an enemy graphic, followed by this fill texture, which is a 1 pixel by 1 pixel white graphic.
White, how convenient. Blends in with everything else.
But the reason for having this pixel is we can stretch it out to fill the bounds of a rectangle and use that as the basis for drawing our, you could say our example, our visual rectangle bounding boxes. And then the last graphic we have is just a graphic of the ship.
And a lot of transparent areas in your two-ship graphic, so we can definitely have a bunch of intersection occurring without any pixel collisions.
Exactly. This whole area in here before you see the actual colored pixels, all of those pixels are transparent, so we should be able to move the two images side by side over here and get no collision until we move over into the opaque pixels.
Precisely.
But knowing that, let's grab our 3 files and jump over to our project folder where we have the newly created per pixel collision project. Inside of that we have the content subproject, which contains a textures folder. So we can paste all of those in. Now back in Visual Studio, let's add those to the project. So we'll go and add existing items. Inside of the content subproject we have textures, and then we have all 3 of our images. So that takes care of image asset data. Now there is one thing we want to add to classes. For this example, I'm going to make an actor class, much as we have in the past. But to begin with, this is going to be a very, very basic version of the actor class. We're only going to contain positional and texture information. That's it. Just about everything else is going to be used for collision.
Okay.
So let's get our actor class started here. We'll add a new item, and this is going to be a class named actor. And then very briefly, before we describe anything inside of it, let me clean up the using statements and clean up the class's subnamespace. So we'll add a using statement, of course, for Microsoft Framework, XNA Framework, and Framework.graphics. So Microsoft.xna.framework followed by Framework.graphics. Now, like I was saying, we'll remove the class's subnamespace, and then we'll take a look at actor. Again, we have some basic things that we want to add information-wise. We want 2 fields for position and texture. I'm also going to add a property, and that property is going to return a bounding box containing the actor. Its information is going to be based on the position and the dimensions of the texture. And then the last thing that I'll add to the basic section of this actor is a draw method, so the actor knows how to draw itself. So to begin with the fields, both of the fields are going to be public. The first is going to be a vector2, and that is going to be the position field. The second is also going to be public. It is going to be a texture2D field called texture. And moving on from that, now we have the rectangular bounds property. So this is going to be a public property of type rectangle called bounds. And again, its job is to return a bounding box positioned about this actor. So it will be a read-only property, and the get accessor will return a new rectangle described by the position and the texture. So return new rectangle. The rectangle's x and y is going to be based off of the position, but of course vector2 components are floats, and we need to cast those to integer to store them in a rectangle. So casting to int, we'll look at the position, and we'll look at the x component. And I'm going to write out this rectangle on individual lines just to give enough room on screen to write it all out. So of course the x component of the rectangle is going to be based on the position.x, or excuse me, y component based on the position.y.
Right.
Of course, again, casted to integer. Now the width and height are simply the width and height of the texture. So looking at the texture field, we feed in its width, and we also feed in its height. And that finishes off our new rectangle. So there's a bounding box to describe the bounds of the actor. Now, one last thing to add to the actor is a draw method. This is going to be a public void method, which we will call draw, and draw is going to need to have a sprite batch in order to accomplish the actual draw. And another quick note to point out is you'll find that the methodology used in coding this example is going to differ a little bit from past examples, in that I'm not going to skeleton in the methods, or at least not going to skeleton in most of them. The idea here is that each individual piece is either simplistic or focused enough that I'm just going to add in the methods as they are needed.
Sounds good.
So this is going to be the draw method, and following our new methodology of implementing immediately, we're going to throw down an implementation for draw, which is simply a call to sprite batch.draw, using the texture for this instance, using the position for this instance of actor, and using the color of white. Now, one thing I will do before we move away from actor and turn our attention to the game class is I'm going to drop down a region which I will leave empty for the time being, called collision. And we'll leave, since I'm going to place all of the collision relevant code is going to belong to the actor, since collision is going to need to look back and forth at things that exist on actor, like position and texture. We're going to need both of those. So we're going to have the actor class itself handle collision. So I'm going to drop this region down, and we'll get back to that later when we start adding collision relevant methods. So now we can turn our attention to the game and set up a few fields in order to describe our little test scene where we have two sprites that we can use for testing. Now the first field is going to be a texture 2D because we need to hold that fill texture somewhere, that 1 pixel by 1 pixel texture. And after that we'll have two actors. We'll name them Actor 1 and Actor 2. And now with these, the next thing that we need to do is to make sure that we load in all of our textured data. So I'm going to move down to the load content method, and we can first address the fill texture. We'll use the content manager to load in a texture 2D from the asset within the textures folder called fill. Now we need to turn our attention to the ship and enemy textures, but I'm not going to store those in texture variables. Instead, I'm going to load them directly into the actors themselves. So that means before we can load in the ship graphic, I need to create one of the actors. So we'll look at Actor 1 first, and we'll create a new instance of actor for Actor 1. Then we can turn around and look at Actor 1's texture property and load a texture into it. And to accomplish that, I'm going to copy the existing content.load line just to speed things up. So in here, we'll change this to point at the ship asset. Now, another thing about that first actor, the one with the picture of the ship, is that is the one that I want to have centered on the screen. And at the moment, if we look back to the draw call we're currently using, we're not specifying an origin, which means that drawing is going to take place at the top left of the graphic.
That's right.
So we need to keep that in mind as we try to center this. Also, we're not going to use any custom or automatic systems here. I'm going to code in magic numbers where applicable, because the point of this video isn't about centering, it's about
It's a
the
proof
collisions.
of concept.
Exactly, it's just a proof of concept, so we'll drop this out as quickly as possible.
And we know it's 800 by 600, so we can just go ahead and divide all that
So
by 2.
So we already have some of the division out of the way. Half of each is 400 by 300.
Exactly.
So Actor 1's position, for that we'll create a new vector 2, and the X component will be the half of the screen width, 400, but now we need to find half of the actor's width, so 400 minus that actor, Actor 1, and get its texture's width, and divide that by 2 to get centered up on the texture's width. So now we can drop down and handle Y, which half of 600 is 300. Then we'll subtract half of this texture's height, Actor 1 dot texture dot height divided by 2, ends off our position. And that takes care of Actor 1. Now we can look at Actor 2. And to speed things up here, I'm going to copy the first two lines where we created Actor 1 and assigned its texture, and I'm going to paste those in for Actor 2. With the only change being that I'm going to have it look at the enemy texture asset.
And of course, there's no reason to set Actor 2's position here because that's going to be controlled by the mouse.
As a matter of fact, we can take a look at that because next step from load content is going to be the update method.
Sounds good.
So from here, if we want to, inside of update, we will position Actor 2, and to do that we need the mouse's location. So I'm going to make a mouse state variable and initialize that to the current mouse state. So we'll use mouse, tell it to get the state, and store that in mouse state. Then we can turn around and set the position for Actor 2. And that will be a new vector 2 based on the mouse's position x and y. So we've got mouse state.x and mouse state dot y. All right, everything actor-wise and informational-wise is lining up, so we can move on to draw. Draw is going to be rather simple. Of course, we have to do our sprite batch begin and end, and then between those, we're simply going to draw each actor. So we're going to take a look at actor 1 and tell it to draw using the current sprite batch, and copy that line for actor 2. You'll notice, of course, we don't have any form of actor list or actor management system, but again, that's not the point of this lesson, so we're not going to encumber the lesson with unnecessary code.
Exactly. So we should be able to build and run it and move a texture around the screen and see the other texture just parked in the center.
All right, well, let's build and we'll try it out. So build successful, and look at that. We have a ship centered on the screen, and we have this enemy texture which I can move by moving the mouse. You'll, of course, notice nothing yet happens when I move them over each other, but absolutely no collision code has been written, so that makes sense.
Yep.
So that means we can now take a look at the first part of the collision system. I guess you could say if it's two-part, then the first part is getting that intersection rectangle between the two objects.
Mm-hmm.
So that means we need to make the intersect method for the collisions. So I'm going to jump back over to the actor class, move down to our collision region, and we can put in the intersect method. This is going to be a public method which I'm going to make static, and it is going to return a rectangle. And we'll call this method intersect. Now, intersect is going to need to take in information in the form of what two rectangles should be considered for the intersection. So we'll feed in two rectangles, a rectangle called bounds A and a rectangle called bounds B. And now you can see where this is made static here. We're not going to call this per an instance of actor. Instead, we're just going to leave it there as a general, you could say, library function where we feed in any two relevant rectangles and get a result back. It just makes a convenient place to organize the function, convenient place to place it. But now, all of the math that we've looked at on the whiteboard is going to come together, well, most of the math that we've looked at on the whiteboard is going to come together in this one method.
Okay.
Here we need to look at those two rectangles, find the appropriate edges to calculate x1, y1, x2, and y2, and make a rectangle out of that new information. So let's begin with some variables. First, we'll look at x1. Now remember, x1 needs to be the rightmost left edge. So here we need to be looking at left edges and find which of the left edges is greater. And an easy way to find which is greater is by looking at the math.max function, so we can get whichever of the two is greater. And the two values we're looking at are bounds A. The two values up for consideration are bounds A dot left and bounds B dot left. So whichever of those two sides is greater gets stored in x1. All right. The next variable will be y1. And to compare those, we're going to use, again, math.max. So I'll find which of these two sides is greater. And the sides that we are looking at are bounds A.top. So we'll drop that in bounds A.top and the top of bounds B.
Wow, this is just so lining up with what we did on the whiteboard.
Exactly what was drawn on the whiteboard. Looking at the two top bounds, find which one has a greater value, and store that in y1. All right, the next variable will be x2. So we'll drop down an integer for x2. Now, x2, that is going to be the right edge of the box. And when we want to select the leftmost right edge. So going left in x is negative x, which means we need to find the lowest or lesser value.
Like I said, I really understand the way you explain it. It's just, it makes my eye twitch every time you say it.
And I was just about to type in math.lesser. It doesn't quite work that way. Math.min works just fine. Math.lesser, not so much. All right, but the values up for consideration here are the bounding box's right edges.
That's right.
So we'll look at bounds A.right against bounds B.right. All right, one variable left. This is going to be y2. Now y2 is going to be looking at bottom edges to see which one is highest or which one is least in y. So we'll look at math.min, and the two edges for consideration are bounds A.bottom and bounds B.bottom. And there we have it. There we have the data necessary to describe the new rectangle. But as we had said before, the rectangle type in XNA takes in a width and a height instead of an x2 and y2. So here I'm going to drop down 2 more variables to describe width and height. Now these 2 variables aren't strictly necessary. Once you have this concept fully under control, it might be easier and take very slightly less memory to not have the variables. But here it makes everything easier to read. So I'm going to make 2 integers, a width and a height. Now what is width going to be for this rectangle? Well, for what we're going to consider a valid rectangle, we always want to have x2 be greater than x1. So we could find the width by taking x2 minus x1, and the difference should represent the width of this new rectangle. And we can do the same for height. Height can be y2 minus y1.
Exactly how it was demonstrated on the whiteboard.
And that was drawn up on the first whiteboard.
And as long as these 2 values are a positive number greater than 0, we've got a valid rectangle.
What happens if we just play with the value we got right now? We've got some numbers, so let's start playing with some stuff.
Okay, sure.
Let us, at this point, return a rectangle based on all of this information. So we'll return a new rectangle. So x is going to be x1 for the rectangle. Y for the rectangle is going to be y1. The width is given in the width variable, and the height is given in the height variable. As simple as that.
Sounds good.
So I'll build very quickly, make sure I haven't introduced any errors. Then back in the game class, let me take a look at how I want to set this up. What I'm going to do here is set up an extra method called draw or debug draw, just so I don't have to clutter the actual draw method with a bunch of code that, were this a real scenario, would be wiping out later.
Okay.
So I'm going to make a private method, no return, called draw or debug draw. And wow on the spelling on that, but alright, there we go. Debug draw. To begin with, the first thing I want to see to make sure it's functioning correctly is this new intersection rectangle. So let's go ahead and use that new method, new static method, and store the result of it in a rectangle variable here. I'm going to call this rectangle collision rect. And we'll initialize that to actor.intersect. And that probably needs to be renamed. Let me see if refactoring will catch it from here. Or did I simply misspell it wrong here? Nope, it's spelled wrong over here. So, okay, very briefly, jump back to actor, and we'll spell intersect correctly. Much better. So now actor.intersect. We need 2 rectangles. Well, we have 2 sprites, two actors that have bounds rectangle properties. So let's look at actor 1. It has a bounds property which we can feed in for bounds A to the intersect method. And we have actor 2, which has a bounds method to feed into the intersect method.
Beautiful. And
this should return a new collision rect. And all that's left is to draw it in some meaningful fashion. So let's look at the sprite batch. Let's tell it to start a call to draw, and we'll draw using our fill texture. And where do we want to draw that? Well, let's visualize that collision rectangle. So we'll feed that over directly into the spritebatch.draw call. So there's our collision rectangle. Now for the color I want here is a color of transparent orange. So I want to be able to see through this texture and see the pixels behind for our sprites. So what I'll do here is I'll make a new color. I can specify the red, green, blue, and alpha components. So for orange we'll have a full value of red, half value of green, no blue, and half alpha. And that should wrap up the call to draw. All that's left is to remember to call debug draw from within the draw method. So call to debug draw, and now we're ready to run. So here we have our sprites as you saw again, and a little bit of a rectangle. So we're already having one small problem. But if we do a proper collision, we can see that as the sprites collide, we have an orange highlighted area describing that collision rectangle. So if we had done the whiteboarded scenario, we have something like this. We have first sprite, second sprite, and a collision between the two. But it also works for the right side, the bottom right side, the bottom left side, or any combination of the two. So we can move all around, even have the texture completely encompassing the other texture, and everything works just fine.
Perfect.
Now the problem areas are what happen when the two are not colliding, when you move the one sprite away.
We have an inverted rectangle.
So that's exactly what's happening. It's inverting. Now we have negative width and height around all the edges. And you'll notice that on some edges it doesn't draw. We still have a rectangle in those cases. I believe it's just a matter of the sprite batch draw call not liking the width being positive while the while the height is negative and vice versa. Mm-hmm. It doesn't like trying to visually describe those scenarios. But all of those scenarios are equally bad for us because we won't be able to tell the difference between a collision and not a collision. So we need to specify a concrete definition of what is a collision from within our intersect method. And that means we need to decide on what is a valid rectangle. Well, as you would describe on the whiteboard, it's any case where we have a positive width and height. And that would be a rather simple check to put in here. We could say if width is greater than 0, and if height is also greater than 0, then return the calculated rectangle. Otherwise, now we'd have to return a rectangle because that is our return type for this method. But if we have an invalid rectangle or an inverted one, what we'll do is we'll return rectangle.empty. We'll use that as our marker to say that there was no collision.
Okay.
So, and also with that, rectangle.empty isn't going to cause any pixels to be drawn within the sprite batch draw method. So here, now we have no inverted or otherwise improper rectangles. However, if we still have the collision, then we draw the rectangle as needed. So really, I think with that's going to wrap up the first part of this demonstration, and then from here we'll move on to the more specific aspects of the per pixel collision detection.
Sounds good. So that's going to wrap it up. Thanks a lot.